In a previous video, we learned that for two-dimensional vector fields F with components m and n, we could tell if the vector field F is conservative if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. We have a similar test for three-dimensional vector fields, and that's what we'll look at in this video. So we have the following theorem. Let F be the vector field with components f1, f2, and f3. If each of those components have continuous first partial derivatives throughout all of R3, then the vector field F is conservative if and only if the curl of F is the zero vector. Now, we won't be proving this theorem, but let's look at some examples to see how it's used. So we want to determine if the following vector fields are conservative. In our first example, F is the vector field consisting of components 2xz minus y, x plus 2yz, and x squared plus y squared. First, looking at the components, I can tell that the first partials of all of these components are continuous. So to check if F is conservative, I need to compute the curl of F. So remember that the curl of F is the del operator cross F. So the first component is the partial derivative of x squared plus y squared with respect to y minus the partial derivative of x plus 2yz with respect to z. The second component is partial derivative of 2xz minus y with respect to z minus partial derivative of x squared plus y squared with respect to x. The last component is partial derivative of x plus 2yz with respect to x minus the partial derivative of 2xz minus y with respect to y. Taking the partial derivatives, in the first component we have 2y minus 2y. In the second component we have 2x and then minus 2x. And in the third component we have 1 and then minus negative 1. So I end up with a vector 0, 0, 2. Now, since the curl of F is not the zero vector, we can conclude that F is not conservative. Let's look at our next example. This time our vector field F has components 3x squared z plus y e to the xy, x e to the xy, and x cubed plus 2z. Again, looking at the components, I can tell that each component has first partial derivatives that are continuous. So to check if F is conservative, I need to calculate the curl. So again, curl of F is the del operator across F. So the first component is the partial derivative of x cubed plus 2z with respect to y minus the partial derivative of x e to the xy with respect to z. The second component is the partial derivative of 3x squared z plus y e to the xy with respect to z minus the partial derivative of x cubed plus 2z with respect to x. And lastly, the third component is partial derivative of x e to the xy with respect to x minus the partial derivative of 3x squared z plus y e to the xy with respect to y. Calculating the partial derivatives, in the first component we just have 0 minus 0. In the second component we have 3x squared minus 3x squared. And in the third component we have to use the product rule. Partial derivative of x e to the xy with respect to x gives me e to the xy plus xy e to the xy. When I take the partial derivative of 3x squared z plus y e to the xy with respect to y, again I need to use the product rule, and I end up with e to the xy plus xy e to the xy. And this simplifies to the zero vector. So that tells me that in this case, F is conservative. Another thing I want to point out is that vector fields whose curl is the zero vector are called irrotational. This term comes from the fact that if I take a ball and place it anywhere in an irrotational vector field, the ball would not spin. Let's consider one last example. Here, F is the vector field negative y over x squared plus y squared, x over x squared plus y squared, and 0. Now I won't go through the details of the calculations, but you will find that the curl of F is 0. However, This particular vector field is not conservative. The reason why the theorem doesn't hold in this case is because the components of f do not have continuous first partial derivatives for all of R3. Specifically, the first partials are not defined at the origin. So if you want to use this theorem, you have to make sure that each component of the vector field has continuous first partial derivatives throughout all of R3. So next, let's look at a summary of things we know about conservative vector fields. So let f be a three-dimensional vector field whose components have continuous first partial derivatives throughout all of R3. Then the following statements are equivalent. First, f is conservative. Second, the line integral of f dot dr is independent of path, meaning that the line integral of f dot dr is the same for any curve that has the same initial point and same terminal point. The third equivalent statement is that the line integral of f dot dr is equal to 0 for any piecewise smooth closed curve C. Remember, a closed curve is just a curve that has the same initial and terminal point. The fourth statement is f is irrotational, meaning that the curl of f is the 0 vector. That's what we talked about in this video. And then the last statement is what we learned a while ago, that f is a gradient field. So there is some potential function little f such that the gradient of little f is our vector field big F. So that's it for this video. In our next video, we'll talk about the dot product of the del operator with a vector field.